Good afternoon, everyone. So, this is my last and final report in abstract algebra. So, I am your discussant. I am Arshel Joy Larry Colot, a Bachelor of Science in Secondary Education, major in Mathematics, third year student. Our topic for today is all about Chapter 23, Finite Fields. 23.1. A finite field or a Gaussian field is a field with a finite number of elements. If F is a finite field, then F has prime characteristic P and contains a subfield isomorphic to Z sub P. Since F has only a finite number of elements that is less than the infinity. We denote a finite field of n elements by a Gaussian field of n. We will show in the next result that n must be a power of p. The result is due to E.H. Moore, 1862 to 1932. The United States is indebted to Moore for its beginnings in abstract algebra and for its initial international recognition in research. Theorem 23.1.1. If F is a finite field of characteristic P and N, then the function of F to G sub P, then F contains P raised to N elements. Proof. Since F is a finite field of characteristic P, has a basis of n elements, say b sub 1, b sub 2, ellipsis b sub n, every element of A of F is a linear combination of b sub 1, b sub 2, ellipsis b sub n, etc. A is equal to A sub 1, b sub 1 plus A sub 2, b sub 2 plus ellipsis A sub 1 plus b sub 1, where A sub I is an element of this G sub P. I is equal to 1, the set of 1 and 2 raised ellipsis in. Now G sub P has P elements, hence F has at most P sub n elements. Since the quantity of B sub 1, B sub 2, ellipsis B sub n is linearly independent over GP, A sub 1, B sub 1 plus A sub 2, B sub 2 plus ellipsis A sub n, B sub n is distinct for every choice of A sub 1, A sub 2, ellipsis A sub n. Thus, F has exactly P sub n elements and the theorem is already proven. Corollary 23.1.3. Any two finite fields of P sub n or P raised to n elements are isomorphic, where P is a prime and n is a positive integer. Proof. If F and F prime are finite fields with P raised to n elements, then they are splitting fields of polynomials x raised to p n minus x over g sub p. Hence, F isomorphism or isomorphic of F prime. The next theorem can be used to show that there exists an irreducible polynomial of arbitrary degree n over g raised to p. Even though its proof is not constructive in nature, it is informative for certain applications. Thus, exercises 5 and 6 can be used to actually count the irreducible polynomials of a given degree. There is an algorithm which can be used to test the reducibility of polynomial over a finite field, namely Berle-Kamp's algorithm. This algorithm is discussed in Isaacs. Corollary 23.1.6. The multiplicative group of a finite field is a cyclic. Theorem. Let F be a finite field and F, the set of A and B, divides F is a field extension with A and B algebraic over F. Then there exists the C element of F, the set of A and B, such that F of F and B is equal to F of C. F, the set of A and B, is a simple extension. Proof. Since F of A divides F is algebraic, then the function of F, set of A and B, is less than the infinity. Thus, if the set of A and B is a finite field, since F is a finite field in a cyclic group with the sum generator say C by the theorem 23.1.5, it follows that F of A and B is equal to F of C. So corollary 23.1.8, every finite extension of a finite field is simple. Theorem 23.1.4, for any prime P, there exists a field extension of arbitrary finite degree n. Proof. Let S be the splitting field of the polynomial f of x is equal to x raised to p sub n minus x over g sub p. Let A element of S be a root of f of x of multiplicity m. Then f of x is equal to x minus a raised to m g of x, where a is not a root of g of x. Now negative 1 is equal to f prime of a is equal to x minus a raised to a minus 1. This implies that x minus a raised to m inverse divides negative 1, whence a minus 1 is equal to 0. Thus, every root of f of x is s multiplicity 1. Hence, f of x has p of n distinct roots in S. Let F denote the subset of S, which consists of all roots of f of x. Let A be element of F. Then, the quantity of A minus B raised to P raised to N is equal to A raised to Pn minus B raised to Pn is equal to A minus B. Therefore, A minus B is element of F, where B is not equal to 0. Thus, F is subfield of S. Since F contains all the roots of f of x and S is generated by the roots of f of x over g of p, F minus S by exercises 6, pages 497, and the theorem is already done. So that would be all for this, and